Well, hello, welcome again to Math 315 analysis and topology, and this is the third recording for chapter 6. So we're about to start looking at this idea of differentiability, what it means to be a function, for a function to be differentiable. And graphically, in school you think about derivatives in terms of a rate of change of a function, or perhaps the one I prefer actually is to think of it as the gradient of the tangent of a function at a point. Now, there are two alternative definitions for the derivative. They amount to the same thing, and I'm going to go through both of these. The one you're probably more used to from high school is the second one, but some books will also use this one, and this can be useful in some theoretical settings. So we take a function f defined on some interval a of the real numbers, and we take some point c, some number c, and we say that a function f is differentiable at c if the limit, this is the limit of f of x minus f of c on x minus c, and we let x go to c. Notice you can't just substitute x equals c in because you get 0 over 0. If that limit exists, or equivalently, this limit, f of c plus h minus f of c over h. This is the one more commonly used at high school. And I'll look at the geometry of that in a second. So if this limit exists, it's denoted by f dashed of c, and it's called the derivative, sometimes called the differential coefficient of f at c. So the two limits given above are equivalent. That is, if either one of them exists, then so does the other. In practice, I will use the second form as in high school, but sometimes the first form, as I mentioned, can be useful in some theoretic problems. So graphically, what's happening in the second limit is this. We've got our function f of x, and we're trying to find the gradient of the tangent at this point. And so what we do is, we're at the point C, we move along a little bit, C plus H, and we then have 2 points here, C, f of C, and C plus H, and f of C plus H. So I've got 2 points here, C and f of C. And we've got another point up here, which is C plus H, f of C plus H. And what we can do is then we can just use the ordinary gradient formula to get the gradient of the secant, and that's just the difference in the y values divided by difference in the x values, which is just h. And that, of course, gives us this formula here, difference in the y values over difference in the x values, or if you will, rise over run is the other way of writing this. And then the clever idea is now to bend this secant around until it forms the tangent. And we do that by letting this point get closer and closer and closer to here. That is, we take a limit as h goes to 0. Now that's a really important concept. That's the way one does it at high school. It's a very fundamental idea of finding the gradient of the tangent to a curve at a particular point. Now I'm going to just do some examples now of this. So we're going to have a look at the how to prove that the function x squared is differentiable at x equals c, and I'm going to do it using both definitions. We know, of course, the derivative of this is 2x, but here we're doing it from first principles. So here it is from definition 1. So we're going to look at f of x is x squared at x equals c. So using definition 1, we look at f of x minus f of c over x minus c. So that's x squared minus c squared on x minus c, and we take a limit as x goes to c. Now, of course, we've got a difference of 2 squares on the top here, so we're going to factorise this as x minus c, x plus 3 divided by x minus c, and at the moment x doesn't equal c, it's just getting close to it, so this is not 0, so I can cancel out these terms, and I just get x plus c, and now as x goes to c, c plus c is just 2c. which is what we would expect from the normal rules of calculus that you know from school. If you differentiate this, you get 2x, and then you plug in c, you'll get 2c. Definition 2, here we're taking f of c plus h minus f of c over h, and we now take a limit as h goes to 0. Now here we can expand out this first bracket, so I get c squared plus h squared plus twice the product of the two terms, that's 2ch, minus c squared all divided by h. So the c squareds cancel, and I can factor an h out of the top, so I get h into h plus 2c, and then I can cancel out the h's, and now h can go to 0 after I've cancelled, and I just get 2c. So that's the first example there. The second one is to prove that f of x is equals 1 over x is differentiable at x equals 2, and I'm going to do this using the second limit. This is the sort of thing which you do with kids at high school. So here is the second example. F of x is 1 over x at x equals 2. So we're using f of x plus h, so replace x with 2 plus f of 2 plus h, so replace x with 2 plus h, minus f of 2, so that's 1/2, and divide that by h. Now clearly I'm going to have to put the top over a common denominator, so I'm going to get 2 minus brackets 2 plus h, and that's going to give me over 2 times 2 plus h, and then I've got an extra h on the bottom. So just, you may have to check that yourself, just checking the algebra here. I've just put them over a common denominator and simplified the algebra down to here. Now the 2's cancel out, and so I just get a minus h on the top, and on the bottom I've got 2h into 2 plus h. And again, the h's, they have to cancel out at some point so you can take the limit. So the h's cancel, and then as h goes to 0, I just get 2 times 2 is 4, and I've got a minus sign on the top. And again, if you were to differentiate this by usual rules of calculus, you will of course get minus a quarter, and x is 2. Now we want to prove, I think, not pause there. So the third example is we want to now look at a function which is not differentiable. So this one here is the absolute value of x, and this is not differentiable when x is equal to 0. And we're going to prove that again using the definition. We'll use the second limit formula. You can see why it's not differentiable. If you draw absolute value of x, you see it's going to have a sharp corner here. It's not going to be smooth as you come through 0. It's going to, you get a nasty jolt if you were to slide down here at that point. So we're looking here at f of x is absolute value of x at x is 0. And we're going to need to look at left hand and right hand limits here because of the absolute value sign. So we're going to look at the limit as h goes to 0 from above of f of 0 plus h minus f of 0 on h. So I plug that in. F of 0 is just 0. F of 0 plus h is f of h, which is absolute value of h, and then divided by h. Now because we're going to h from above, that means the h values we're looking in here are positive. So I can replace the absolute values. So absolute value of positive numbers, just the number itself. So I can remove the absolute value sign as long as h is going to 0 from above. That gives me h over h. The h's cancel, and I just get a limit of 1. So as I approach 0 from this side, the gradient is getting closer and closer to 1. On the other hand, if I do it from the other side, I do exactly the same calculation, f of 0 plus h minus f of 0 divided by h. And now I'm looking at the limit as h goes to 0 from below. And when I simplify again, I'm just going to get absolute value of h on h. Now if h is negative, then the absolute value of h is of course minus h. And when the h's cancel, and I then take a limit, I'm going to get minus 1. So the left-hand limit is, the right-hand limit's 1, the left-hand limit's -1, so the limit does not exist. So the limit as h goes to that does not exist, and therefore conclusion is f is not differentiable. F is not differentiable at x is 0. We get that again from using the definition. Okay, so you need to be able to do some basic derivatives like this. This next one is a harder example. I wouldn't expect you to be able to do this one, but this is a harder example. I'm going to use the trigonometric identity. Sine of x minus sine y is 2 cos the average times sine of the x minus y on 2. This is a formula from trigonometry. If you've done some trig, you might like to think about how I got this in the first place. It's not a one that you have to memorize or know. I don't think it turns up in the school syllabus, but it's not one the students have to know either. But we're going to use this to show, using the first limit definition, that sine of x is differentiable at any point c. So we come back to here's the solution of this. So here's our function, and we're going to need a basic result. We did this one before, that if you take a limit as t goes to 0, we proved that sine of t on t goes to 1. That was our standard limit that we proved a while ago. And I've just copied down here this trig identity that we were given. Sine of x minus sine of y is twice cos the average times sine x minus y on 2. So we're going to be looking at, I'll just remove that little bit of mistake there, that's better. So we're looking at using the first definition, so it's f of x minus f of c on x minus c, and we take a limit as x goes to c. So that's sine of x minus sine c on x minus c. Now I'm going to use this formula here, so x is x and I'm replacing y with c. So I'm going to get 2 cos x plus c on 2 from here, times sine x minus c on 2 from here, and I copy that one down. Now the trick at this point is to say, well, this bit here, this is okay when as x goes to c. We've got problems here and here, but this is okay. So I can plug c into here, so I get c plus c is 2c divided by 2 is c. So I'm just going to get cos of c here from this term, and I'm going to take that one out. So I'm taking this bit here out. This bit here is okay as x goes to c. So I take that out, that's cos c. Now I've got this 2 left, and because I've got x minus c on 2 here, I want x minus c on 2 on the bottom. So I'm going to take the 2 downstairs and write it like this. So that 2 is coming right down here, double-decker fractions, it's coming right down here. Now what I can do now is I can relabel this x minus c over 2, I'm going to call that t. So I'm going to get sine t on t, and then as x goes to c, t is going to 0. And this is our limit we mentioned before. This limit is 1, and so I just get cos c. So there's a little slightly more difficult proof there that the function sine of x is differentiable everywhere. Okay, well, geometrically, another way of thinking about these derivatives is these definitions say that the function has a tangent at c, that's one way of thinking about it, or that the graph of f looks roughly, without a t there, looks roughly like a straight line, provided you're in a sufficiently small neighbourhood of c. Another way of saying this is that a differentiable function can be closely approximated by a line near the point at which the derivative is found. So for example, if I were looking at x squared in this little tiny interval, so this is now from minus 1/10 up to 1/10, then if you plug this into here and substitute some values in, you'll find this is very small. So the graph is sort of looking something like, roughly like that. And it's almost flat. So near the point 0, provided we magnify in, we're looking at very small numbers here, then the graph is approximately a straight line near 0. And that's one of the things we mean by a function being differentiable. It can be closely approximated by a line near the point at which the derivative is found. So this is almost a straight line near 0, near the point 0. And if you've got a graphics calculator, you can have a go at drawing that on this interval and you'll see what I mean there. Now sometimes we've got functions that are only defined on intervals, or they're piecewise defined, and so we need to worry about how do we handle derivatives at endpoints. So to deal with endpoints, we're going to define the left and the right hand derivatives as follows. And again, there'll be two definitions for each. Generally, we're going to use the first one. So the right-hand derivative, that means we're approaching from the positive side, from h going to 0 from above, or x going to c from above. We're going to write that as f little plus dashed of c. This is the right-hand derivative at c. And it's simply the same limits we had before, except we're taking right-hand limits in both cases. Similarly, we can have a left-hand derivative, f dash with a little minus there, where we take a limit as h goes to 0 from below, or x goes to 0 to c from below. In our calculations, we're mainly going to use the first one, the first limit formula. So I've just done one example of this one. And this one here is we're going to find the right-hand derivative of x to the 3 halves at x is 0. Now the point here is that if x is negative, this doesn't exist. So this function only makes sense if x is positive or 0, because the on2 here, the fraction half, means we take the square root of x, so the x has to be positive. So this will have a right-hand derivative. It won't in fact have a left-hand derivative, but as we approach 0, we'd like to know what exactly is happening to this thing. In fact, if you draw a graph of this, which I'll do on the solution here, if I draw a graph of this thing, the graph of this function, it looks something like this, and it will have a derivative as we go towards 0, and we'll see it in a moment, but the function's not defined for negative values of x, because we have to take a square root because of the 2 here. So for the right-hand derivative, well, we just go back to our definition. We're looking at x as 0, so we've got a limit as h goes to 0 from above, and it's f of 0 plus h minus f of 0 on h. So that's f of h, which is h to the 3 halves. F of 0, when you put 0 in, you just get 0, and divided by h. Now h to the 3 halves over h is just h to the 1 half by the index laws, and then h can go to 0 and you just get 0. So in fact this is coming in and it's making a gradient of 0 as it gets closer and closer to there. So this function has a right-hand derivative. There's no left-hand derivative, but it's got a right-hand derivative. Now just a little bit of notation. In some books you will see this notation used, this delta x. They use that in place of h, and they use delta y in place of f of x plus h minus f of x. Personally, I don't like this particular notation. I would generally suggest you avoid using it at school, because students will get confused here. It doesn't mean delta times x, it simply means a small change in x. It's much safer to use the h notation. and the f of x plus h minus f of x. But you will find some books use these deltas here. In other words, I can write the derivative then as the limit then as h goes to 0 becomes the limit as delta x goes to 0. And this was my delta y, that was this quantity, divided by h, which was delta x. And then when you take a limit of this one, that's where the dy dx notation comes from. This notation was used by Leibniz. And he then wrote dy dx as the limit as delta x goes to 0 of delta y on delta x. The only advantage of this is you can use it to prove the chain rule, and it's used in change of variables in integrals, but it's also very confusing because this delta x does not, you can't cancel the deltas out. It doesn't mean that. It means a small change in y and a small change, corresponding small change in x. And these cause a lot of grief at school, so I generally would avoid using these in high school maths. It's false to say that some people then talk about this delta x and delta y as infinitesimals. Well, there are no such things, as we'll see when we look at the real number system. Newton called them fluxions, and Bishop Berkeley later parried them as ghosts of vanished quantities. Since such objects do not exist on the real line, we'll come back to this much later on. So this term infinitesimal should not be used. You can formally define what an infinitesimal is, but that's much more complicated. And to start talking about infinitesimals in the context of high school maths it's just not right and very dangerous. Anyway, when we write such things as delta y is f dashed x delta x, what we really mean is that a small change in y is approximately f dash times a small change in x. These are thought of as small but non-zero quantities. In general, I suggest you avoid ever writing these things. Now, differentiability is a very strong condition, as the following theorem shows. Our theorem says if f is a function defined on some interval, then if f is differentiable, then it's automatically continuous. If it's differentiable, then it automatically has to be also continuous. Now that is important because that means if the function's not continuous at a point, then it can't be differentiable. So you have to check continuity first. Now the proof of this is actually fairly straightforward because I'm just going to use our limit definition of continuity. So f of x minus f of c, we do our usual trick, we divide by x minus c and multiply by x minus c. The point is then that this quantity here, as x goes to c, this is going to the derivative because the function's differentiable, and this is going to 0. And that means then that the limit, that means as x goes to c, f of x minus f of c goes to 0. And that's the same then as saying that that then says that the limit as x goes to c of f of x exists and equals f of c, and this is just the condition for f to be continuous. So note then, for a function to be differentiable at a point, it firstly has to be continuous. And I'll do some examples of this in the next recording.